Today we are working through differentiation past paper questions. So what I've tried to do is select a few questions that give a good representation of the different things that you'll come across while you're doing differentiation-based questions. So jumping right into it, the first one, we've got the curve y equals 10 over 2x plus 1 minus 2 intersects the x-axis at A, intersects the x-axis at A, y equals 0. The tangent to the curve at A intersects the y-axis at C. Intersects y-axis means x equals 0. Show that the equation of AC is 5y plus 4x equals 8. Then find the distance AC. So, in order to show that the equation of AC is 5y plus 4x equals 8, what we have to do is find the equation of AC, and then magically, if we do it correctly, we will find that our equation matches that. For a show that, we're going to be always doing the question and then matching. So we've got our equation of our curve. We're working with a tangent. Remember, the gradient of the curve equals the gradient of the tangent at the specific point. So we're going to need to know, in order to get the line of this tangent, we need the gradient of the tangent. We can get that from the gradient of the curve. And we're going to need the location. We're going to need this point A. So let's start off by locating A. Okay, so for location of A, we know that we're crossing the x-axis at A. So the curve is crossing x-axis at A, so y equals 0. So 0 equals 10 over 2x plus 1 minus 2. We're doing algebra here. We're solving an equation. So we keep in algebraic form. Multiply through to clear our fraction. 0 equals 10 minus 2, 2x plus 1. Take a step to open the brackets. Minus 4x minus 2. So 4x equals 8 and x equals 2. So now we know that the A is the point 2, 0. Make a note, and then it's there, it's obvious, and it's easy to use later. So now we've got the location of A, we want to work towards getting that gradient. Because we're aiming for y minus y1 equals mx minus x1. That's what we're always going to use when we're creating the equation of a line. So in order to get the gradient of the tangent, we need to do the gradient of the curve. We now have to go into calculus format. So y equals 10, open bracket, 2x plus 1 to the minus 1 minus 2. Now we are in calculus form, we're ready to differentiate. In order to get our gradient, we need a dy by dx. dy by dx equals ax plus b. We have a linear core here. So we have 2, 10 minus 1. 2x plus 1 minus 1 is minus 2. And when we differentiate minus 2e, it disappears because it's a constant. We simplify, minus 20, 2x plus 1 to the minus 2. Right, now we need the gradient of tangent. So for gradient of tangent, we know that we're working at the point A. So, at x equals 2, dy by dx equals minus 20. 2 times 2 plus 1 to the minus 2, which is minus 20 divided by 5 squared, which gives us minus 4 over 5. Okay, so that is our gradient of our curve. And we can also say mt equals dy by dx at A. Therefore, mt equals minus 4 over 5. Because remember, we're always making that link. We're not just randomly plugging numbers into things. We're communicating. Why did we do this? What are we doing next? So, Gradient of our tangent equals that. So now we can do equation of our tangent. We have our point, A is 2, 0, and we have our gradient, minus 4/5. And then we use our magic-friendly, wonderful formula. Y minus 0 equals minus 4/5, x minus 2. So here our fraction, 5y equals minus 4x plus 8. 5y plus 4x equals 8, and that should sound familiar because, way back up here, show that the equation of AC is 5y plus 4x equals 8. So if we work through each of our steps, we've got to the same answer as them. So therefore, we have shown completely independently, we have shown that this is what the equation of that tangent is. So now back up to, gets to part 2, find the distance AC. Okay, so we've got A, 2, 0. Take a note of that. So A is 2, 0. Where is C? The tangent to the curve at A intersects the y-axis at C. So, for location of C, we have 5y plus 4x equals 8. We are cutting the y-axis, so x equals 0. At x equals 0, 5y equals 8, so y equals 8/5. So now we've got the point C is 0, 8/5. Now we can do the length AC. AC equals the square root, distance formula, coordinate geometry, it's coming back. Okay, so we've got 2 and a 0, so we very simply 2 squared plus a 0 and an 8/5, 8/5, all squared. All squared means that fraction goes into brackets. That means you have an 8 squared over a 5 squared. This we're just going to plug into a calculator one time. AC is going to equal, in exact form, 2 root 41/5. Okay, so now what do? Because normally in pure maths, we leave an exact form, but that is a really clumsy surd. It's not sort of like a 2 root 3 type of answer. So in this case, I would leave it in my exact form, but also give it to 3 significant figures, which is 2.56. If we go back to our question, there is no indication given here about whether we should do 3 significant figures or exact form. It doesn't say anyone is specified. So in this case, we've hedged our bets. We've covered both options. We've got exact and rounded. And that's that. So that differentiation was key to finding the gradient of our curve in order to get the gradient of our tangent, in order to get the equation of our tangent, in order to work with the equation of our tangent. Our next question is something that we flew through past a little bit in the last lesson, looking at increasing and decreasing functions. So here we're told that a curve has an equation, and it's a cubic. Show that the gradient of the curve is never negative. So in this case, we would have to show the gradient is always positive. So we need that gradient. So we have y equals 3x cubed minus 6x squared plus 4x plus 2. Okay, calculus format already. For gradient function, we need dy by dx equals 3 times 3 is 9x squared minus 12x plus 4, 2 disappears. Now, remember, if you want to see if it's an increasing or decreasing, you can't have this x squared and x. If there's a quadratic ax squared plus bx plus c, you've got to put it into completed square format first. So what's quite interesting is that this one is a fun one, okay? Because we have a square number here and a square number here. So this is actually just 3x minus 2 squared. Now, some of you might be freaking out at that concept. Others of you are quite happy with it. Okay, so for those of you who are freaking out, let's see how it works, okay? So we take out our 9. X squared minus 4 over 3x plus 4 over 9 is ugly, but we'll work with it. So 9, now we complete the square. X plus a half b, so minus 2/3, all squared. Minus a quarter, b squared, 16 over 9, plus c. Okay, exactly how we've always done it, equals 9. X minus 2/3, all squared, and when we combine all of this, it disappears, because we have minus 4 over 9 plus 4 over 9, which actually just gives us 9 minus 2 over 3 squared. But you see how this 9 is a square number, right? Laws of indices. X minus 2/3 squared. Now you see, these are both squared. So here's the fun and games. We can say 3x minus 2/3 squared, because it's the same thing backwards. If we put the squared in, it would go in on the 3, it would go in on the bracket, so we can take it out. Remember all those laws of exponents you can use backwards or forwards. Now, because the exponent is tucked out of the way, this equals 3x minus 2 all squared. Magic. Okay, so when you've got square numbers involved on both ends, you can have some funny games. If you want to do it the slow way around and work with your exponent laws, there's absolutely nothing wrong with it. Okay, so at the end of the day, our gradient function is this, 3x minus 2 all squared. So how does that show us that the gradient of the curve is never negative? Well, the thing is that it doesn't matter what value we put in here. If we put in a 2, if we put in a minus 100, if we put in a positive 1,000,000, whatever value we put in is going to give us a value in here, which is then going to be squared. And whenever we square something, it is always positive. So, for all values of x, 3x minus 2 squared will be positive. Therefore, the gradient is never negative. We have shown what they asked. Okay, so in order to answer any gradient question about a curve, whether it's a stationary point or an increasing or a decreasing, we need that gradient function. Then we need to look at the question, we need to look at our gradient function, and we need to think about how can we get to an answer to our question. In this case, we got gradient function that's a quadratic, so we need to take it into completed square format before we can conclude about what happens when we put in different values of x. Are we happy? Okay, people are looking good, so let us talk about the next one. We've got some geometry going on. Okay, so the idea here is to look at applied question. So we have a picture, we have a diagram. The diagram shows a plan for a rectangular park, A, B, C, D. We've got all these measurements on it. Points, these and that are on this and that, and these are paths that surround a triangular playground. The length of dy is x, and the length of xc is 2x. Show that the area, a meter squared of the playground, is given by that. Given that x can vary, find the minimum area of the playground. Okay, so starting off with part 1. Show that the area of the playground is given by this. So area of the playground, rectangle minus 3 triangles. So rectangle is easy. A equals 40 by 60. I must be careful of my handwriting size here. This triangle here, What's this length? Remember, it's rectangle, so all of these are right-angled triangles, making our life easier. Well, if this is 2x, and this is all is 60, this is 60 minus 2x. Same thing on this side, if this is x, this is 40, then this is 40 minus x. So we're going to cut out those triangles, so we have a minus a half So minus a half times 40 times 60 minus 2x. We have a minus a half, that's that one, we'll do this one next. 2x times 40 minus x. And then we want to get rid of this triangle as well. So minus a half times 60 times x. A lot of numbers, so let's simplify each one separately. So 40, 60 gives us 2,400. Minus a half times 40 times 60 minus 2x. Well, the half times 40 gives us 20. So minus 20 times 60 is minus 1200. Minus 20 times minus 2x gives us plus 40x. Next one, minus a half times 2, well that just gives us minus. So minus x times 40 is minus 40x. Minus x times minus x is plus x squared. And the last one, minus a half times 60 times x is a minus 30x. And you see how it looked ugly, but now it's looking not nearly so ugly? So, putting it into our normal quadratic format, ax squared, so x squared, plus bx, plus 40x minus 40x, poof, disappears, minus 30x, 2,400 minus 1,200 is plus 1,200, oh, magic, x squared minus 30x plus 1,200, let's be proper, put our a's in, and we have shown that the area equals that. So if you are having a particularly sleepy moment and you couldn't show it, they've given it to you so you can still do part 2 of the question. But it's nice to have that 2 marks there. Okay, so part 2. Given that x can vary, find the minimum area of the playground. Those are both indications that you're working with applied differentiation. So we have a equals x squared minus 30x plus 1,200. Given that x can vary, the playground is going to vary, so the area of the playground is going to depend on x. So dA by dx. Doesn't it just work beautifully? Differentiating. X squared becomes 2x minus 3x becomes minus 3, 1,200 disappears. So dA by dx is 2x minus 3. Now the minimum area is going to be the stationary point. Minimum is a stationary point. So where gradient equals 0, where our derivative equals 0. So minimum at dA by dx equals 0. Tell them where you're going. Tell them the point of doing all of this. So 2x minus 3 equals 0. Oh, 2x minus 30. And nobody has shouted. Goodness gracious, that's shocking, ladies and gentlemen. This is minus 30x. This is 2x minus 30. This is 2x minus 30, and this gives us x equals 15. Shocking. Make sure you're awake when you come for maths lessons, because then you can catch the moments when I'm not awake. Okay, so we have our minimum at x equals 15, but that's not what they asked us. They asked us, what is the minimum area of the playground? Okay, so we need to know what a equals when x equals 15. So at x equals 15, a equals 15 squared minus 30 times 15 plus 1,200. So A is going to equal 975 meters squared. Okay, it's an applied question, so we have an applied units. And I hear that some people aren't shouting because they are trying to keep up. Okay, so if I'm going too fast, then please shout, because I know I do sometimes work very fast. Okay, so I will pause for a moment, give you a moment to collect yourselves before we go on to the last question. Are there any questions out of this already? Are we happy with applied differentiation and the questions before it? Okay, so I know that some of you aren't also necessarily at this stage. Okay, so bear with me, but it seems like everybody has caught up. So we shall move on to the next question. I gave myself lots of space for that one. Our last question for today is another applied one, looking at something a little bit more interesting. So we've got a lot of information here. The volume of a spherical balloon is increasing at a constant rate, bells are ringing, of 50 centimeters cubed per second, bells are ringing. Find the rate of increase of the radius, bells are ringing, when the radius is 10 centimeters. And then they're so nice to you. They tell you that the volume of the sphere is 4/3 pi r cubed. So I wasn't lying when I said that the less usual shapes come with instructions. So when we read through this, we came across a few different things. We came across a volume. We came across time. We came across radius. And we came across rate. Now, when we're talking about rate, we are talking about a derivative. So this is a chain rule question. We start by saying, who are our variables? We have V equals volume in centimeters cubed. We have T equals time in seconds. And we have R equals radius in centimeters. Okay, sometimes, I think once in maybe more than a decade, they've done something fun with the units. But it's always worth writing them down, and then you know, have they done something fun, or am I just working straightforward? This one's straightforward. Seconds, centimeters, centimeters cubed. Next thing we always do for a chain rule question is we write down our rates. Centimeters cubed per second. So that is volume by time. So dV by dt equals 50. They gave it to us. Find the rate of increase of the radius. Well, that would be dr by dt equals, we don't know, that's what we're looking for. So there's always a third rate. We're usually finding one, given one, and differentiating for one. So the other way, we've got a v and a t, we've got an r and a t, so the relationship that's missing is the v and the r. So if we think about the v and the r, we've got v equals 4/3 pi r cubed. So we have v equals 4/3 pi r cubed from our question. So now we've got that relationship between v and r. We can get dv by dr equals 3 times 4/3 gives us 4. Pi stays the same, he's a constant. R cubed becomes r squared. So now we've got 3 rates. So we know now we have to look, what's our chain? We also have to bear in mind that we have an unknown r here, but we're told r is 10. So at r equals 10. So our chain, we want the one that is on top and on bottom. So who's on top and on bottom? We have a dr on top, we have a dr on bottom. So they belong on the right-hand side together. So our chain here is dv by dt equals dr by dt times dv by dr. Then we can plug in what we've got. So 50 equals dr by dt we're looking for, times 4 pi 10 squared. We don't want another unknown in there, and we know what r is. So dr by dt equals 50 over 400 pi. So dr by dt, we do not want to leave our fraction unsimplified, 1 over 8 pi. Straightforward and simple fraction. It is exact, so we would leave it like that. In this case, we're not going to take it to three significant figures. We weren't told to, so we won't. We'll leave it as the rate of increase of the radius with respect to time is 1 over 8 pi, and it's going to be centimeters per second. So rate of increase of radius equals 1 over 8 pi centimeters per second. Applied question, applied answer. So when it comes to chain rule, you've got your little story, but a large part of the answer to the question is decoding that story and figuring out what variables am I working with, what rates am I working with, and how do they relate to each other. So the challenge in a chain rule question is that breakdown of the question. So if you work through it systematically each time, then you've got that information available. And you can go for it. We could sit here for the next 4 lessons and do just differentiation questions, because there is a very wide variety in what they can ask. So unfortunately, we don't have another 4 lessons just to do differentiation at the moment. So we're going to move on to integration in the next lesson. If you have any still questions with differentiation, then shout if anything was unclear. Also, make sure you find out what the problems are and the solutions, because once you've got differentiation sorted, then it's a much easier transition into integration.